Section 8.3, Bonding Theories. So what we're going to do is we're going to talk about this idea of the VSEPR, or some, VSEPR theory, that helps us figure out the shapes of different molecules. So you might want to jot that down, but that's kind of the key thing we're going to talk about in here. And you recall, we've talked about how we have different orbitals and stuff, and we have the S sublevel and P sublevels and so on. And these are pictures from ones that we've done before. And that's when we're talking about electrons running around an atom. Well, now let's talk about what happens when they overlap. And when they overlap, we produce molecular orbitals versus atomic orbitals. And the molecular orbital is occupied by 2 electrons. That's what holds these atoms together. This is the bonding orbital. So these particular new bonding orbitals have particular shape. We have two main kinds that they talk about: sigma bonds and pi bonds. And as far as importance of this, this isn't what I would say is one of the high priority things, but just be familiar with the idea of what this is. And these are an example of sigma bonds here. And notice that on all of these different examples, and they're different ones, whether they're S's overlapping or P's overlapping and so on, but they're all around the axis of those 2 atoms that we're talking about that are bonding. So on the top one, you can see you just kind of have an oval around the axis between the 2 nuclei of those things. That's what sigma bonds are. They're the bonds formed around that. Pi bonds, on the other hand, are not around the axis. So notice how we have 2 P sublevels that are overlapping each other, and we're getting some bonding. That's the green here. And notice that there's one's above and one's below the axis line where the nuclei would be. And so those are called pi bonds. So that's the difference. That's sigma bonds are around the axis, pi bonds are not. All right, let's get into more of the VSEPR theory and talk about shapes and stuff. And you've done some of these by now. And in the CH4, methane, we have a tetrahedral angle. The angle is actually 109.5 degrees if you were to measure it. And you can see the picture on the right. That's an example of a tetrahedral molecule of CH4. Well, the VSEPR theory stands for valence shell electron pair repulsion theory. In other words, kind of my translation is electrons don't like each other and they want to get as far away as they possibly can. They're going to repel each other and get as far away as possible. Okay, so they're always going to adjust the shapes to give themselves the biggest possible shape away from each other that they can. And if you look at this example here, most times if I give people like 4 toothpicks and a ball to stick the toothpicks into, they're going to put it at about 90 degrees. But to be honest, you can get farther apart. If you think in 3 dimensions, you can put it at 109.5 degrees. So that's the difference here. You can get them farther. You got to think 3-dimensional as you're doing this. So let's take a look at ammonia, NH3, and the bond angles in ammonia are 107. Now notice that and here's a picture of kind of how it's going to look, but notice that it's a little bit less than what it was in CH4, and that's because there is an unshared pair of electrons, and unshared pairs of electrons are actually stronger as far as forcing things down. So they actually force the molecules a little bit lower on the scale there than they were in the tetrahedral or the CH4 molecule. If we go to something like H2O, which has bond angles of 105 degrees, that's even smaller because, once again, now we have 2 unshared pairs. So they're stronger, they push it down even farther. If we go CO2, we have bond angles at 180 degrees because we've got unshared pairs on both sides, but we have the same number, so they're equally strong, and the farthest that they can get apart is 180 degrees. So let's talk about some of the shapes that you can get out of these. The first shape is linear triatomic. So we're just talking about the ones on the left there, not the ones on the right. The ones on the left are linear. They're triatomic. There's 3 elements and they're a straight line. Another example would be trigonal planar. And these would be, when they're talking about planar, it means that it would lay flat on the table. So these are bonded in such a way that they actually lay flat. If you were to build this out of the ball and stick models, it would lay flat on the table. So it's triangular shaped but lays flat. That's trigonal planar. Then bent triatomic is the water molecule. That's the one that looks kind of like that. It's still flat. It still would lay on the table, but it's bent triatomic is what they call it. Pyramidal would be like ammonia, the NH3 molecule, and it's going to stand up, and if you kind of filled in the sides, you would get like a three-sided pyramid. Then you have tetrahedral. That's like the methane molecule. That's going to look like that. And it also looks like a pyramid, but it's got an extra molecule or atom in there. And so, you've got, they call that tetrahedral because there's like four parts that stick out from the central part. Trigonal bipyramidal kind of looks like that. So you can kind of looks like a pyramid on the top and the bottom. So that's kind of bipyramidal. You have octahedral, which is going to look something like that. So you get like an 8-sided figure if you were to put that all together. Kind of looks like two tetrahedrons. Square planar is going to look like that, where it's once again planar means it's going to be able to lay flat on the table. And T-shaped, our last one here, is going to look like that, and that would also lay flat on the table. So those are some possible molecular shapes. You need to understand from drawings on paper what the shapes are going to be, and that's why we did it. We built those with models, but you have to think about, well, where are my unshared pairs of electrons? In this particular example, there wouldn't be unshared pairs of electrons. It wouldn't turn out like that. So this is kind of a little bit different. Somehow they're not like that. It's probably got a double bond and then a couple single bonds or something. So you've got to take a look at where those unshared pairs of electrons are, understand that they would actually create some bend. They would push those other electrons away and try to come up with the shapes that are there. All right, that is it.